The term natural ventilation is used to indicate the intentional airflow through openings obtained without the use of fan or other mechanical devices. It is created by pressure differences caused by the wind or by temperature differences between the inside and the outside. Natural ventilation affects health because of the relationship between air changes and air quality. The energy balance of the building, since the flow of external air subtracts heat from or adds it to the internal space and to the building structure. Thermal comfort, because air velocity affects the body's energy balance through convective exchange and perspiration. In this lecture, we focus on some indication about air movements inside and around buildings and on related basic principles. First of all, air always moves naturally from a higher pressure zone to a lower pressure one. An airflow is called laminar when the speed is low and the fluid streamlines all move in parallel. As the speed increases or a pronounced change of direction occurs, the motion becomes turbulent and fluid streamlines cease to move in parallel, giving rise to significant changes in direction and to eddies. Air is subjected to the Bernoulli effect, because of which there is a reduction of pressure when speed increases. This effect is exploited in the wing of an airplane, whose shape is such that it forces air passing above it to follow a longer path. This results in greater speed than that of the air flowing beneath it. The pressure at the top is then lower than at the bottom, and there is a push from the bottom to upwards. Because of the Venturi effect, when an airstream is forced through a smaller section, its speed increases. As an effect of a combination of the factors previously described, when the wind hits a building, it causes area of low pressure to be created along the side parallel to its direction and on the leeward side. When the air inside the room is warmer than the outdoor air, it triggers the stack effect. The pressure inside is lower than it is outside due to the lower density of the warmer air. It must be clarified that it is not an easy task to predict the flow of air around and through buildings, especially with regard to the path of the fluid streamlines. In the past, knowledge in this field was mainly built up with scale models, smoke tests and wind tunnels. More recently, computerized fluid dynamics allows designers to predict with very good accuracy the effects of their choices. However, some indication deriving from the previous experiences could help architects in early design stage. For instance, it is well known that when a low-rise building is to windward of a higher one, considerable turbulence is created between the two. In building of stilts, leeward pressure is reduced, and in correspondence to the stilts, wind speed significantly increases. To maximize the cooling effect of the wind, trees with high canopy should be used and bushes should be kept away from the building. The airflow pattern due to the wind depends on the relative position of the openings. The best conditions are created when outlet openings is higher and wider than the inlet. The ideal is to have them of equal area. An horizontal overhang above opening deflects flow upwards. If the overhang is spaced away from the wall, the flow is deflected at half height. When inlet and outlet openings are aligned, cross ventilation is activated by wind. If the openings are aligned in the direction of the wind, the airflow passes right through the space, influencing a reduced part of it and giving rise to modest induced air movements. If the wind blows obliquely, however, the ventilation involves a wider zone and more air movement is induced. If the wind blows parallel to the openings, there is no significant air movement in the space. If the room has openings on adjacent walls, wing walls can significantly increase the effectiveness of natural ventilation. Note that in the picture, green circles represent a higher pressure zone, while red ones mark the lower pressure zones. In most cases, rooms have only one wall facing outside and a single opening. Ventilation is derived only from turbulence induced by wind fluctuation, and the resulting air movement is quite poor. In fact, if the window is on the windward side, the available wind velocity is about 10% of the outdoor velocity at points up to a distance 1/6 of the room width. Beyond this, the velocity decreases rapidly and hardly any air movement is produced in the leeward portion of the room. This situation can be improved by splitting the single openings into two, positioning the part as far apart as possible. If the wall is to windward, a further improvement is obtained by constructing a vertical fin. In conclusion, the shape of the building, its layout and the surrounding environment affect air movement, and they should be properly considered in the evaluation of natural ventilation features.